Okay, I think I'll start. Hi everyone. Today I'm going to talk about exploring base preconfirmation without gateways. I'm Lin Oshitani from Nethermind Research. Okay, so in this talk I'll go over what base rollups and preconfirmations are, give a quick recap on that, then talk about our Taiko preconfirmation POC work, then talk about multiple preconf PBS solutions. I'll explain later what that actually means. Then briefly touch on fair exchange problem, and then talk about next steps. So a quick recap of base rollups and preconfirmations. But before that, let's talk about rollups. So rollups scale by posting transaction data to L1, but executing them in L2. So if you look at it, you can think of it as L1 blocks containing L2 blocks within it, like that. So the big question here is, okay, how do we build these L2 blocks? And how do we build the blocks is a fundamental question in Ethereum research. And so it's only natural that even in the L2 context, this question is being asked. So most rollups today, they build their blocks using a centralized sequencer. So a user sends transaction to a centralized sequencer will collect a bunch of transactions, and then eventually posts a bunch of L2 blocks to the L1 block building pipeline. And then the L1 block building pipeline will construct a block that contains these L2 blocks. And a nice thing about centralized sequencers is that they can provide preconfirmations. What preconfirmations are is that it's like saying that, hey, your transaction that you just send over like that, I'm going to include your transaction in this specific position in the L2 block eventually. So you're going to give a promise. The centralized sequencer is giving a promise. And then eventually, after some time passes, they will actually construct submit a bunch of L2 blocks to the L1 block pipeline, and will be including like that. The preconfirmations are nice because it gives really good UX to the user. So the users can get immediate confirmation of the transaction in a speed of light speed. However, they are centralized. So a big question in L2 is how do we decentralize the centralized sequencer? Okay, so one idea here is, okay, this centralized sequencer entity, what if we just remove this role entirely? And this comes this leads to the idea of based rollups. So the idea is of based rollups is let's use the L1 block building pipeline to sequence not only the L1 transaction but also the L2 transactions. So user sends the transaction over through the L1 block building pipeline itself. This is both L1 and L2 transactions. And then eventually the L1 block building pipeline will construct an L1 block that contains the L2 blocks too. Okay, let's expand this L1 block building pipeline part. So L1 block building pipeline, using the MEV supply chain diagram that Flashbots introduced, it looks like this. The user sends the transaction over, and then searchers who, for example, if it's a DEX trade, they will insert arbitrage transaction right after it and construct what's called bundles. And then the searcher will submit those bundles to the builders. And then the builder will collect a bunch of these bundles and create a block. And then this block will be there'll be many builders within the same slot. They're all going to compete over this block proposal. And then they're going to send a bunch of bids to the proposer. Proposer selects the highest bid, and then publishes an L1 block. And now here, let's see that the whole pipeline is not only for the L1 transactions, but also the L2 transactions, which are colored in red here. Okay, so base rollups have really nice properties. First, they inherit the L1 censorship resistance and liveness, because we don't introduce any additional centralized entities to this whole pipeline. So there is no centralized sequencer here. So as long as L1 is live and L1 is not censoring, the L2 transactions are also not censored and live. And it also, another nice property is it provides L1 composability, because L1 transactions and L2 transactions, they are sequenced by the same entity. In this case, the builders. So these L1 builders, they have full visibility against the L1 transactions and the L2 transactions, and they can sequence them in a way that can, for example, provide atomic execution guarantees. So in other words, the builders can act as like centralized, as shared sequencers. Okay, however, base rollup, they have a problem and they are slow. So you need to wait L1 slot times for any form of confirmation. So the user, the end user, you have to wait until this like final L1 block is actually published to know what the result of their L2 transaction was. And builders cannot provide preconfs, at least like a strong form of preconf, which gives strong guarantees, because they do not have monopoly over the sequencing rights. So like the builders, there's many builders competing over the right to construct this L1 block. So any single builder, they cannot like say that, hey, I'm gonna 100% win the auction and propose the block so I can provide you pre-confirmation. Like nobody can do that. So how can we provide pre-confirmations in a base rollup setup? Here's like the idea of base pre-confirmations. So base pre-confirmations, the insight is very simple. Like, okay, the builder does not have monopoly, but this proposer, the L1 proposer that sits in the end here, they do have like monopoly sequencing rights. So they're the ones that are like doing this final sign-off of the like the L1 block that also contains L2 blocks. So they do have the ability to provide pre-confirmations. So this is like base pre-confirmations. The idea is simple. Like L1 proposers can opt to provide pre-confirmations during their slot. So here, this proposer, like let's assume that he is like opted in to provide pre-confirmations. And in that case, the user can directly send over their L2 transaction to the proposer, and this proposer can directly like respond with a pre-confirmation. And then like the proposer will keep on providing pre-confirmations, collecting L2 transactions, constructing L2 blocks, and then eventually, when the slot ends for the proposer, they can force the builder to include these L2 blocks within the L1 block. I'll talk how this works later. And then finally, the L1 block with these L2 blocks that were like pre-confirmed will be published. Okay, however, like since preconfs like requests, okay, this is simple, but however, since preconfs are requested via end-to-end RPC calls, so like these proposers, they have to have like an open RPC endpoint somewhere, so like the users can actually connect to and send pre-confirmation requests. And also, like it's expected to be responded per transaction at like a very fast rate, like speed of light, under 100 millisecond like latency. So this makes like providing pre-confirmations requires a lot of sophistication as a result. So like gateways are introduced. So the idea is simple. Like gateways, proposers delegate their pre-confirmation duty to gateways ahead of their slot. So ahead of their slot, the proposer will say, hey, this specific gateway, this is a gateway that is gonna like do my pre-confirmation duties. So instead of sending over your transaction to me, like please send it to the gateway. And this delegation relationship, for example, it can be recorded in the L1, some L1 contract. Now the user will send like transaction to the gateway will provide pre-confirmations, and then eventually the gateway will like, collect a bunch of L2 blocks, construct a bunch of L2 blocks, send it back to the proposer will ensure that it's included in the L1 block. Okay, so this is all nice. However, there's some problems. So now, like, the system includes an additional centralized entity, the gateways, which weaken the inherited L1 censorship resistance and liveness. And note here that this gateway, it's like locked in ahead of time, like, because the proposer need to like explicitly state that this is my gateway, so please send over your transaction here ahead of time. So it's a much more stronger lock-in than the builder auction that's happening in the L1. And because it's a ahead of time lock-in, I would like argue that it's going to be much more reputation-based, and then much more like have a much stronger centralization like pressure. Furthermore, like with separate block building entities for L1 and L2, as in like now the L1 transactions, they're like sequenced by the L1 builder, and then you have this like L2 gateway that's sequencing the L2 transactions. Now you have like these two different pipelines for the block building. So the shared sequencing part is kind of like diminished here. So it makes achieving L1 composability become much more challenging. So like it's kind of like weakening like both of the like very strong benefits that we had for based rollups. Okay, so now like we were listening a lot like about this gateway and like how are there any way to not introduce it, at least in the first like iteration. And here, let us me introduce like pre-confirmation POC we did for Taiko, which is a gateway-less design. So a quick recap, like pre-confirmations require sophistication, but why did it require sophistication? Because it required like end-to-end RPC calls to request the pre-confirmations, and also like responded per transaction at like 100 millisecond, like less than 100 millisecond latency. And these were where the sophistication pressure came from. So instead, by having preconfs, like first requested via L2 public mempool, so instead of like directly accessing the gateway or the preconfer or the proposer, you just send it to the existing L2 public mempool that Taiko has. And then, like, let's say that instead of responding per transaction at like speed of light latency, let's respond per L2 block at 1 to 3 second latency, for example. And in the following slides, I'll take 3 seconds as example, but like the seconds can be lower after some experimentation. And by making these two like modifications, we can enable pre-confirmation without gateways. So let's see how that would work. So the idea is simple. Like during the slot, L1 proposers will construct L2 blocks from the L2 mempool every 3 seconds and publish them. So in this diagram, first the proposer will collect a bunch of L2 transactions from the public mempool and then construct an L2 block and then publish it. And this like published L2 block, it will be published to like a pre-confirmation P2P. Anyone who's listening to this P2P, they can actually execute these L2 blocks, know what exactly like transactions are included and how they're executed, and know the exact result of the transaction. Now this process will be repeated every 3 seconds during the L1 slot duration. Every 3 seconds, the proposer will collect a bunch of L2 transactions, construct an L2 block, and then publish it. So at the end of the slot, like 4 L2 blocks are constructed because like we have 12-second windows in the L1, and if you like construct L2 blocks every 3 seconds, that's 4 L2 blocks. Now at the end of the proposer slot, the proposer sends the builder the L2 blocks for first inclusion. The proposer will send, hey, the builders, if you want to win my like auction, you have to include these L2 transactions because I have already like pre-confirmed them and like promises that I will include them. And for this part, we use Bolt. Because Bolt's like forced inclusion like APIs. Okay, and then like in the end, the L1 block building pipeline will publish an L1 block that includes these L2 blocks. So our preconf POC is like a maximally simple pre-confirmation solution. Like it's a solution that's kind of depicted in this like very simple diagram. And it's always good to start simple, I would say, like in general in software engineering. So this is like the initial version that we're starting off with. However, like proposer may eventually want to outsource their pre-confirmation duties to external actors. This might be to reduce the operation cost, like because like it's in L2 block level, like pre-confirmations using like mempool, like the operation cost is like much lower than other designs. However, there is still a cost of like constructing the L2 blocks and publishing it to a P2P. They might want to like reduce that cost. Furthermore, they want to like extract MEV from these L2 blocks being constructed, and extracting MEV like requires sophistication. And they might want like to enable L1 composability. One thing I did not touch on is like here, you see that these L2 transactions and the L1 transactions, they are like also like not sharing the pipeline anymore, and it makes L1 composability much more harder. So you might want to like use PBS to re-enable that. So here they might want like pre-confirmation PBS. So they might want to like delegate the pre-confirmation duty to an external actor. So let's touch on pre-confirmation PBSs. So like there's multiple ways to do this, and one way, actually the gateway is like one way of doing this. So like you fully delegate the pre-confirmation duties to a gateway ahead of time. This is what we like previously like introduced. So this is like one way of PBS because like you're delegating the L2 block building rights to a gateway. So these have like multiple pros, which it can provide like super fast 100 millisecond pre-confirmations, like because the gateway will be sophisticated, and they will have like these public RPC endpoints where people can like see send their transactions. And also have potential for better revenue. So this connects to like Connor's like more talk in the morning, where because this gateway has like monopoly sequencing rights over the 12-second window, they can actually like maximize the profits over the 12-second window, like because they're like incentivized to do that. And in other designs that I'll touch on, like it's not always this case. And also it has like this and oh yes, so like the gateway can maximize its revenue, which is nice. But a con is that, okay, it's like centralization. Like this gateway, it has centralization pressure on it. And also the complexity in the L1 composability, because as I mentioned before, like the block building pipelines are not shared anymore. Okay, so now another way would be to have an L2 PBS. So have an L2 specific PBS pipeline that runs every 3 seconds. So here you have like the L1 PBS pipeline. This will run every 12 seconds as usual. But then you can have like a separate L2 specific PBS like builders and searchers. And the pipeline in the above, it can run every 3 seconds. And then after every 3 seconds, it can like construct an L2 block and keep on doing that, and then like have all the L2 blocks that were pre-confirmed included in the L1 in the end. Okay, the pros of this is that it runs a just-in-time auction for preconfs. So like the builders are all building for the right of proposing these L2 blocks. So you don't have a lock-in into a specific gateway ahead of time. So you retain the just-in-time auction part of PBS in L1 that we have in L1 PBS. It's nice, but the cons is that yes, as I mentioned before, like you have like 2 separate block building pipelines, so the L1 composability is made like harder. And also that L2 MEV revenue might not be optimal. So this again like connects to Connor's point where like because these builders, they're going to be incentivized to maximize the revenue that they create in these individual L2 blocks. So instead of maximizing revenue over the 12-second window, every 3 seconds they're going to try to maximize revenue if they're like own locally built blocks. So this might not match. Like these locally built L2 blocks that are maximizing revenue, if you add them up, the revenue will most likely be lower than like having monopoly power over a 12-second window and constructing like maximally profitable block over the 12 seconds. Okay, so another like way of providing like PBS pre-confirmation PBS is what we call like Mr. MEV Boost, or it's an acronym for multi-round MEV Boost. So the idea here is like, okay, this whole L1 block-in pipeline that we had in base rollup setup, let's instead of like running it once in the 12-second window, let's running it every 3 seconds. Like run the whole L1 block-in pipeline, this PBS pipeline, every like 3 seconds, for example. Now the nice thing here is that you do not have like additional actors, like there's no gateways or like L2 specific builders or all that. And another nice thing is that now you are sharing the block building pipeline again between the L1 and the L2. So it can give like better L1 composability. However, the cons is that it changes the whole L1 block building pipeline. So like that is like a huge complexity because like the L1 it's already like running right now. And like touching that, it will be a lot of effort. And the L2 and L1 MEV revenue will not be optimal anymore. So L2 MEV revenue not being optimal, it might be fine, because like they're not capturing any L2 MEV in the first place. Like we're just introducing this new pipeline. But for the L1, it's going to be much harder because they are like the L1 proposals are like having maximal like revenue for the 12-second window. So like reducing that, it's going to be like much harder. So you might probably want to like restrict the kinds of L1 transactions that you can pre-conf, so that like the revenue hit is like small. Or have some floor price of having a floor price for the pre-confirmation tip, for example, like to mitigate that. Okay, so like our Taiko POC, I see it like EV in Pokemons. So in Pokemon, there's this Pokemon called EV, and this EV can like conditionally evolve into different, like, so it has a branching evolution structure where it can evolve into different Pokemon depending on some conditions. So our Taiko POC work, it's like a maximally simple version of preconfirmations. And if you want to add on top like PBS, like you can like have a gateway design or like L2 PBS design or Mr. Map Boost, but this all depends on like what the market needs and like what kind of like further research is made. And I think like starting with a maximally simple design and later evolve it, I think this is like in general like a good design principle. Okay, let me also briefly touch on fair exchange problem because I think it's very important. So like the problem here is how do you enforce the timely release of preconf? So like I've mentioned like this whole pipeline where the proposer build L2 blocks and publish it every 3 seconds. But how do you enforce like the timely release? After 3 seconds, this L2 block is actually proposed because like the proposer, they're incentivized to not actually preconf. Like they want to delay it as much as possible. At the maximum case, they want to wait 12 seconds prior no preconfirmations. And the 12-second time, like they like look at the full mempool and construct like the most optimal like L2 blocks. So there, the proposers are incentivized to not provide preconfirmations. Like how do you force that? So this is like the fair exchange problem. So nice thing about our POC approach is that it introduces a natural heartbeat to the system. So every 3 seconds, these L2 blocks, it has to be published. And this is going to be like very visible to all the participants that are connected to these like preconf P2P. So like what we need is like some way to monitor this heartbeat. So who should monitor then? Like, and for this, I think we can take an iterative approach. So first, we can say that, okay, these proposers that are providing preconfirmations, we can only allow a whitelist of proposers to actually preconf. So this is far from ideal because it's like whitelisting, it's permissioned, but I think it's a good way to start to like get something into mainnet and like test it out. And then eventually we can shift to a guardian approach where like the guardians have the right to blacklist like proposers who are missing their heartbeat. And the nice thing about like this like heartbeat is that it's going to be very visible whether like the proposer is like withholding the heartbeat or not. Because anyone who's connected into P2P, they can know whether this proposer is like actually withholding the heartbeat. So if the guardians are like malicious and they like start to blacklist random proposers, that's also going to be very visible too. Because there's going to be social pressure that the guardians are not going to like blacklist random proposers. However, it's still not ideal because yes, you do have like this guardian who has like a lot of power. So eventually, in the end, we can get to a world where the end users are monitoring. So the end users can monitor these heartbeats, like these L2 blocks being proposed. More accurately, the full nodes that they're connected to, the L2 full nodes that they're connected to, they can monitor. And then the end users can stop sending order flow when the preconfers are missing their heartbeats. So like this preconfer, he's supposed to be providing preconfs like every 3 seconds, but he's not. So I'm going to stop sending my L2 channel altogether to the mempool. This will mean that decrease the order flow to the proposer, and it should disincentivize like the proposer to do this. So here again, I'll introduce a Pokemon analogy. Like I think here we can take a gradually evolve the design that decreases some trust assumptions. So we can start with a very like whitelist approach, which is like very simple, but like a lot of trust assumptions. Then we can eventually evolve it to guardians and then end user monitoring. And I think like this kind of iterative approach is also like a good practice in general. Okay, next steps. So we have extended our collaboration with the Taiko team to continue working on our POC. And our next milestone will be to bring our POC to mainnet, so make it like mainnet ready. And our focus would be to keep the core design like simple as possible while solving like essential issues such as the fair exchange problem and the on-chain cost reductions. In conclusion, like base rollups are great. They provide L1 security and composability. But L1 preconfs are also great. They bring good UX to the base rollups, but they bring like centralization pressure and complicates L1 composability. But as we went through, there are ways to address them. And our Taiko POC, we start with a maximally simple design and we'll incrementally evolve and we'll continue taking this approach moving forward. Okay, here's a bunch of references and that's it. Thanks, everyone. Questions?
Nice presentation. I appreciated starting with a simple model and building up an intuition. I thought that was very helpful. I noticed, though, in a lot of the diagrams, you did not have the relay identified. And I might be off base here, but my understanding was the relay could be a natural fit to play the role of the gateway. How do you see that as part of the design? It seems like that could be a more natural market structure that just develops based off of what already exists today.
Yes. So yes, like as you correctly point out, like I'm omitting the the relay here, and like the gateway. Yes, like there's a lot of discussion that the relay will be a natural like entity providing like acting as a gateway, and there's like the reasoning for that is that because the relay they already have this like good connection with the proposer. They also have like very good DevOps, so like they're going to be a natural fit. But I'm not 100% convinced that the relays are like going to be like the best fit, or like simple relays are going to be best fit for this, because like these L2 transactions, you will have to price them, right? You have to like make the decision whether you pre-conf or not based on like the lost optionality that you're going to eventually get by like providing that pre-confirmation. So pricing is going to require sophistication, like, and like a very simple relay that's just like receiving transaction and immediate responding, like that will not be profitable. So, and this sophistication, it's more of a sophistication that you have in a builder or a searcher. So yes, like entity-wise, it might be the relays that are going to run this, like, but still, like the sophistication that's going to be required there, I would say it's going to be like closer to builders and searchers. That's my like intuition around that. Yeah.
Yeah, thanks for the talk. In one of your designs, you mentioned a public L2 mempool. Could you elaborate on who are the nodes in this mempool and what's their incentive to maintain it?
Yes. So this L2 public mempool, this is coming from Taiko. So Taiko right now, what they have is like this like maximally simple like usual-based rollup, and they already have this like public mempool that's running. And this so right now, if you want to like submit a Taiko transaction, you're actually submitting to the Taiko public mempool. Anyone in the network can construct like collect these transactions from the Taiko mempool and submit it through the L1 block loom pipelines. This is what's happening right now. And so yes, so in pre-confirmations, what I'm saying that let's just reuse what's already existing. We already have this Taiko public mempool, so let's use that to also like receive pre-confirmation requests too.
A follow-up, if I may. Is this public mempool somehow like related to, I don't know, L1 mempool? Because it's like a bit unclear for me who exactly runs this.
Yes, so it's going to be Taiko nodes. So like anyone can run a Taiko node and connect to this public mempool and like contribute to the gossiping and all that. But it's going to be separate from the L1. So L1 public mempool, it's going to be separate. These Taiko L2 mempool is going to be maintained by these L2, like the Taiko full nodes that are like around the network.
Thank you.
Hey, Lin, thanks for the great presentation. Can you go back to the fair exchange slide and maybe talk a little bit about where you guys are in your fair exchange related journey and what's next a little bit more?
Yes. So we are like actually like planning to take this approach that we are mentioning here. So for the like immediate Taiko POC like mainnet mainnet ready like version, we're thinking of just going with a whitelisted proposers. And this is like not just for the fair exchange, it's also like because we might have bugs in this like the whole system and like just to be safe. So yes, basically, and the next 2 points, it's more in the research phase. we are like planning to go with whitelist, but like what's the next step? Me personally, I think like the Guardian approach would like make a lot of sense, but this is still in the research phase.
Okay, thank you.
I also have a question regarding the fair exchange problem. Like, you mentioned that you require the pre-conference or the proposers to send a heartbeat, right? But even if a proposer like sends a heartbeat, like for an L1 block, you divide an L1 block into like 4 L2 blocks, right? But even if I as a proposer send a heartbeat for the first L2 block, but it doesn't contain any transaction. So how do you solve that problem, and how do you prevent the proposers that only send the L2 block at the very last slot, but
Yes.
three blocks before don't contain any transactions?
Yes, so that's a good point, and this is actually something that I omitted from the presentation. But yes, as you mentioned, like the proposer, they can just like submit 3 empty blocks, and then in the 4th one include the whole thing and like maximum extractive MVV and all that. This is possible, like in the what I just described. So an additional thing that you need here is like kind of an intent structure. So the user, when they send their transaction to the like mempool, they can condition it saying that, hey, my transaction, it has to be included within this heartbeat, or this like next heartbeat, or next heartbeat. So it's going to be, and then if you don't include it by then, it's going to be expired. So if the proposer is like just emitting like empty L2 blocks and then try to include it finally, a bunch of transactions will be expired at that point. So like this monitoring system, it does require this kind of intent be baked into the transaction, saying that, hey, after these many heartbeats, I want my transaction to be like expired. So yes, that is something that was missing, and yes, that was a good point.
One quick follow-up question, like how are you like addressing that in the current like POC?
Oh, so the fair exchange problem. So the fair exchange, like in the POC, we haven't like tackled it yet. So it's kind of like left to the proposer to actually like provide these pre-confirmations, and it's not like we don't have that expiration mechanism that I just talked about. So it's just mathematically simple. So that's why this is fine for when we start with a whitelisted proposer, because like we're just trusting them to do it. But then yes, our next step will be to include this kind of like expiration mechanism and actually enforce it in the protocol level. So
Thank you.
thank you.